Dear students, good evening. Welcome to this session. GTQ. Dear students, through questions. Good evening. Welcome to this session. All are fine. GTQ. Dear students, through questions. Hope your preparation is going well. Welcome to this session. All are fine. So we have your session through questions. Your preparation is going well. Welcome to this session. All are fine. So we have your session through questions. Your preparation is going well. Welcome to this session. All are fine. So we have your session will help you. Your preparation is going well. Welcome to this session. All are fine. So we have your session will help you. Your preparation is going well. Welcome to this session. Kindly let me know how was the audio. Hope everything is fine. So we start with the question. Usually, when you deal transformers, you will commonly have a confusion how to take the voltages given here as V or E. How to take them exactly. This is a common confusion you will have in solving questions. There you will be stacking up. I want to deal that particular doubt in this particular session. I want to give you a clarity because it totally depends on the question, how it is made. It totally depends on the context and what you are asked finally. You will understand when I solve this question later. Now, 3 single phase 50 kVA 6351 by 230 volt 60 Hz rating transformers are connected to form 11 kV by 230 volt 3-phase transformer bank. The equivalent impedance of each transformer referred to low voltage side is 0.0012 plus J 0.0016 ohms. The 3-phase transformer supplies a 3-phase load of 120 kVA 230 volt at 0.8 power factor lagging. Find the primary voltage. Find voltage regulation. Like this, 3 single phase transformers are there, means 3 primaries, 3 secondaries, 3 high voltage primaries, 3 low voltage secondaries. Those 3 high voltage primaries are connected in star or delta. These low voltage secondaries are connected in star or delta, finally to form a bank, a 3-phase transformer bank transformer, right? If you observe the question, it is given like this. 11 kV by 230 volts. The transformer, single phase transformer 6351 by 230. Observe the secondary single phase means per phase obviously by default 230 volt 230 volt, which means generally whenever you say 11 kV by 230 volt 3-phase transformer, by default it is line voltages, that's it. Wherever you listen these 33 kV, 11 kV, these all are line voltages only. Unless it is not specified in the question very clearly that they are phase voltages, you should by default take as line voltages only. That 11 kV is a line voltage, 230 volt is a line voltage. On the top 6351 per phase voltage, actually 230 per phase voltage. So what does it imply is 230 implies the secondaries are connected in delta, because in delta line is equal to phase. That is obvious. But the primaries are definitely not in delta because it is 11 kV. So simply we can say it is connected in star. So what we can say now is this three-phase transformer bank is connected in star delta mode. So across a phase 6351. As this is star, across a phase 6351 means across the lines root 3 times 6351, it is 11 kV. So 11 kV. That side, the three transformers, three low voltage secondaries are connected in delta. And you know, across every phase 230 volts. And obviously, as it is delta, line voltage is also 230. This is what is the question is all about. Now this transformer has given like this, R value, X value referred to LV side. And the question contains there is a load of 120 kVA across this three-phase transformer. Here there is a load, three-phase load, 120 kVA. So first what we'll do is we'll calculate what are the currents in the windings which help us to solve the question easily. 120 kVA at 230 volts, and you know root 3 VL IL is equal to 120 kVA. So as it is secondary side, load side I am using 2. So IL2 is equal to 120 to 10 cube by root 3 into V230. Then IL2 value is voice. Let's check. Someone is asking why we are not using power factor. This is 120 kVA. It is not 120 kilowatt. If it is 120 kilowatt, then when you say kilowatt, that is VI cos phi. VA means simply V into I, because it is 3 phase, root 3 VL IL, or 3 V phase I phase. Hope you understood. So when you're dealing with volt amperes, just kVA ratings or volt ampere ratings, you need a power factor. In kilowatt only you need that. Don't get confused. So we got the line current. Whenever we are dealing delta side, there is a relationship between line current, phase current again. We should not forget it. This is IL2, that is 301.235. Now, if you want to calculate the primary side voltages or currents using K, using turns ratio K, then what is required is phase values. For this transformer, what is turns ratio means? Remember, when you're dealing with 3-phase transformers, compulsorily you should remember one thing: phase values. Remember always one thing: whenever you listen to turns ratio N1 by N2, in single phase, as the name itself tells you phase, single phase, it is always phase value only. There is no meaning in telling line or phase, everything is same there. But whenever you are dealing with 3-phase transformers, you must say compulsorily the turns ratio means per phase values only. For example, this is phase value, this is phase value, phase value, phase value. So whenever you're defining K, turns ratio K, here phase value by this phase value. So 6351 by 230, that is this. So whenever you're dealing with the voltages referred to this side from that side, you should always multiply with phase values only, not with line values. If you want line value, then depending on the star or delta connection, you can make into root 3 or by root 3 currents and voltage respectively. So what I want to convey is, using K, if you know what is the current here, first, phase value. So the phase value here is 301.235 by root 3. Because this is a delta connected transformer, the phase current is by root 3. Then the value is I phase 2, value is 301.235 by root 3, 173.923. So once you know what is the phase current in this particular secondary side, you can easily use K and you can calculate the phase current on primary side by K. If there is a current here, I phase 2, what is the current in the primary means I by K. So on that basis, we have calculated now I phase 1. What is I phase 1 means? 6.3 amperes. In simple words, because of the load connected across the secondary 120 kVA, the current flowing in the primary, here line is equal to phase, the current is finally 6.3 amperes. Now, the transformer equivalent circuit referred to primary side. Why primary side means, if you notice the question contains primary voltage. So I'm going to primary side, but already the impedance is referred to LV side. So when the impedance is belonging to LV side, if you want to refer to primary side into K square. So these are the equivalent resistance and reactance referred to HV side. Then HV side current is 6.3 amperes. Now the question is, first it contains find the primary voltage because of that load. Find the primary voltage means it implies what is the voltage we have to apply across the primary in order to achieve rated voltage across the secondary. That you have to understand. Whenever you are asked find primary voltage, you have to find this. Means this is a known value actually. As the circuit is referred to HV side, low voltage referred to HV side, you know V2 into K. This is V1 dash, that is V2 into K. And this can be directly taken as 6351 volts. And you know equivalent circuit is always a per phase equivalent circuit. Always. So per phase value only we are dealing with that. So this is known now. because you are asked the what is a primary voltage, you have to fix this is known. In order to maintain 6351 voltage across the load, irrespective of what is the loading condition, that load for a given power factor, what should be the primary voltage? That's the context of the question. So you have to make it unknown now. V1 is unknown here. So the current is now given 6.3 amperes at an angle, because the load is at a power factor 0.8 lagging. So minus 36.87. So if you solve, you will get an answer. So this should be the primary voltage across the transformer. It implies in order to maintain rated voltage across the load, across the given load. That's the meaning. Next, voltage regulation. In per unit, it is no load voltage minus full load voltage by full load voltage in percentage into 100, that is 6360.22. On no load, that's the voltage, because this voltage is exactly here on no load. With load, when current flows, there is a drop and the voltage will be that. That's the meaning. Minus 6351 by 6351. Full load voltage means rated voltage always. The value is, better we make it percentage. In this question, you are given voltage ratings and you are asked what is the primary voltage. In this question, you have seen how we have calculated the primary voltage according to the given load conditions. If you see the next question, and after combining both concepts, you will get clarity how to deal transformer voltages, primary, secondary, according to the question and the context asked. So you have seen one way of solving the question. Next question I'll be solving in two ways so that you will get a full clarity on this concept, and the confusion what we get generally, how to take the voltage ratings of the transformer V1 or E1 accordingly, will be cleared. A 10 kVA 400 volt by 200 volt single phase transformer with a resistance of 3% and reactance of 6% is supplying a current of 50 amperes to a resistive load. The value of the load voltage is, in the previous question, what is the primary voltage asked? So we have selected load voltage as 6351 and we have calculated for a 6351, that is rated voltage across the load, what is the primary. In this question, if you read, you are asked what is the load voltage, which means 200 volts. You should not answer. It doesn't imply 200 volt is the load voltage. What you have to do now is you have to think 200 volt is the voltage on no load, and definitely because of that resistance and reactance there is a drop for sure. Due to drop, the terminal voltage will be definitely reduced. So simply we can calculate using voltage regulation, that is one way, or by making equivalent circuit also you can deal. Both I will show you. Finally you will get a crystal clarity on the concept. Because it's a resistive load, I'm making it plus only. You know this formula already, voltage regulation, because the resistances and reactances are given in percentage already. I'm using it, percentage R, percentage X. So is equal to R percentage is given 3%. As the load is given clearly resistive, means cos phi is 1, sin phi is 0. That's why simply here 1. This is equal to 3%. Voltage regulation for the given transformer is simply 3%. Why 3%? Because of the loading, resistive load, we have done it. Next, so you know voltage drop is VNL minus VFL. No load voltage minus full voltage is voltage drop. So voltage drop by V rating is taken as voltage regulation. So this is equal to 3%, it is given, means 0.03. So voltage drop is 0.03 into V rating. So what you can do now is simply V rating, as you can take 200 volt, is the voltage drop. The terminal voltage is This is generally what you think. By using voltage regulation we can solve the question, one pattern. I'll be giving you one more concept. In the question it is, what is voltage across the load? There is some load, pure resistive load, due to which a 50 ampere current is passing. So 50 ampere at an angle 0 resistive. Then what is the voltage across the load? That is the question. So this is a known value obviously, because this you have to calculate, anyone should be known. So you can take now 200 volt as this side. Now you have to correlate. In the previous question they asked what is the primary voltage, so you have kept this known value and you have calculated it. In this question what you are asked is what is the load voltage, so you have to calculate. This means this is unknown and this will be known value. You have to put here 200. Understand the logic. According to the question, data, context, it will vary. Next, here RLV, XLV, because this is belong to LV side. This transformer 400 by 200 volt, right? So that is LV side. And what you are given here are percentage values, 3%, 6%. Easily you can calculate them into actual values. So this information, like the what I solve now, also helps you to solve some other set of questions involving per unit, actual values, base values. You know already one thing like this. Per unit value is equal to actual by base value. So actual value in ohms is equal to per unit into base value, and base impedance is V square by VA. And if you are belong to a particular side, then that voltage you have to put. For example, base impedance on LV side, that is Z base LV is equal to 200 square, because LV side is 200, by what is the transformer rating given here? 10 kVA, that is 10,000. The value is 4. Percentage by 100. RLV value is 3%, right? 0.03 into 4. XLV is 0.06, 6%, I think, right? Yes, 6% into 4 base value. So the value is 0.1 to 0.24. So RLV is 12 ohms. This is ohms. In this way also you can calculate. So the question is, what is the load voltage? Voltage across the load. Then given in the question 200 volt side. So this is the transformer equivalent circuit referred to load side, LV side. So 200 I'm putting here and I have to calculate this. So simply we can write V2 is equal to 200 minus the current given in the question is 50 into R 0.12 plus J 0.24. If you solve, you will get a magnitude 194 point something volts. Point you will buy plus percentage x sin phi is approximate voltage regulation formula. If you can recollect the theory what we discussed in the class, when we draw phasor diagram for deriving the voltage regulation expression, we will use a word approximate voltage regulation by ignoring a small value, a small length we ignore in the phasor diagram for convenient analysis sake. Because here we are not dealing with all those phasor diagrams directly, we are calculating using KVL, you will get more accurate value, and that doesn't matter actually. You will get almost the same numbers, only decimals will change. If anyone think why a small change in decimals, I am explaining that. So finally you got an answer 194 volts. This is another way to solve. Hope after seeing these two questions you got a clarity how to take the voltage ratings given in the transformer questions according to the data context. Someone is asking again a doubt. In the previous question, you are asked, what is the primary voltage? So, unknown is primary voltage, means you have to take the given value across the load and you have to calculate it. Means you have to maintain that across the load and to calculate the unknown, that is primary voltage. In this question, you are asked, what is the load voltage? When you are asked what is the load voltage, again you can't say 200 is the load voltage. By giving you the value, they won't ask you again the same thing. Now 200 should be taken not as load voltage, because they are asking you what is load voltage. Calculate what is load voltage by putting 200 as here, no load voltage. Then you can get the voltage across the load. According to question, you have to solve it. What's the difference between three-phase transformer and a three-phase transformer bank? When we start three-phase transformers in the class, we discuss like this. First three-phase transformers idea, the first case is like taking three single-phase transformers and combining them as a three-phase transformer. Means if you take three individual single-phase transformers, three primaries, three secondaries, total 6 terminals will come this side, total 6 terminals will come that side, 3 windings will come, every winding has 2 ends. Take these 3 windings, connect them in star or delta. Take those 3 windings, means those 3 secondaries, high voltage primaries, low voltage secondaries, or low voltage primary, high voltage secondaries, anything, and connect them in delta or star. If you have 3 individual single phase transformers connected as a 3-phase transformer, then it is called as a bank. 3-phase transformer is not 3 individual transformers. If you go out on a road, if you come out of your apartment, you will see a transformer as a distribution transformer. It is not a bank. It is not a combination of 3 units. Bank means 3 individual units, 3 individual tanks. You will see 3 individual things there. That's a bank. When all are combined together, that we'll see in the theory, not here. Hope this is enough for you to understand what is a bank and what is a unit. A single phase transformer has no load loss of 64 watt as obtained from an open circuit test. When a short circuit test is performed on it with 90% of rated currents flowing in its both LV-HV windings, the measured loss is 81 watt. The transformer has maximum efficiency when operated. So this is a common question you will see commonly in the exam. Condition for maximum efficiencies. You know already at which kVA, at which load factor, at which load, percent load or per unit load, maximum efficiency occurs. You know the formula already. The formula is here, remember, it is full load copper loss. Rated load, full load, both are same. Copper loss is that. The twist in this question is the copper loss what is given. You know, in short circuit test, the wattmeter reading is basically copper losses. So the copper losses what you are seeing in the question 81 watts is not obtained at full load or rated current. It is obtained only for 90% rated current. Means 90% means 0.9 per unit, right? So as copper losses are square of the current, vary as square of the current, think like this. 0.9 square, because of that 90% is producing 81 watts, means there is not rated current, 90% only. Full load means 100%, means 1 produce how much? Because the copper loss vary as square of the current, we can relate like that. So finally, what is full load copper loss means? watts. Remember this commonly in the questions of transformers, open circuit test, short circuit test. Generally, short circuit test must be conducted at rated current concept. Then only rated copper losses will be coming. In the same way, when you think about induction motor also, blocked rotor test also must be conducted at rated current only. Then only the wattmeter reading can be considered as rated copper losses. While you are solving the questions, sometimes they will ask you efficiency for rated conditions. Sometimes. But they won't provide you the short circuit test or blocked rotor test data, wattmeter reading or copper losses for rated current. So you have to check it. If you check it is exactly for rated current, okay. If it is not given for rated current, what you have to do is take at which current it is given. That square is the data given to you. Then full load current square, how much? You can equate that and finally you can calculate accordingly and you can solve the question. Auto transformer is one of the important concept for GATE. Commonly asked questions on auto transformer. I have taken one case here. You know, a two-winding transformer can be reconnected as an auto transformer. If you go to the previous GATE questions, you will see commonly asked a two-winding transformer reconnected as an auto transformer. Different things will be asked. One of the commonly asked question is, what could be the maximum rating as an auto transformer? Already two-winding transformer has a particular rating. It has voltage ratings and power ratings. Obviously current ratings. You should not violate voltage rating and current rating in the windings when you reconnect it as an auto transformer. That's common. That's like a rule. You can't violate the voltage. Insulations issues will come. You can't violate the current because already the winding cross sectional area is designed for a particular current rating. So for the same voltage rating, for the same current rating, you will notice one thing. Auto transformer power rating is not at all same as two winding transformer rating. It will be a definite difference here. A significant difference will come. Now you can connect a two winding transformer as an auto transformer in various ways. Total 8 ways are there. In that you can subclassify as 4 ways. Step up, step down. In each way, step up, step down. 4. Totally 4 concepts. Like 4 possible ratios or connections you can see here. For example, this is 400 volt winding. This is 100 volt winding. And the rating of the transformer is 10 kVA. So 10 kVA, 400 volt side. What is the current rating means? You can say 25 amperes. 10 kVA, 100 volts. What's the current rating here is 100 amperes, you can say. Now, if you notice here, HV, LV. If you want to connect two winding transformer as one winding transformer called auto transformer, 2 windings must be connected in series. And one portion of the winding is common to both input side as well as output side. That is called as common winding. So you can make a common winding, low voltage winding or high voltage winding. First, let us make common winding as low voltage winding. See, LV as common to input side as well as output side. And one thing, while you connect the windings in series, imagine a connection in this way, plus minus kind of thing. You know, dots are representing same polarity. Dot notation importance is that same polarity they will convey. Let us take, for instance, this is plus and this is plus. So if this is dot, this is undotted. If this is dot, this is undotted. Just imagine how you will put remote cells in your TV remote or any toy or a bat somewhere, some toy. Plus minus, they all add. In a similar way, plus minus, they all add. Additive polarity it is called as. LV common, additive polarity. This is one mode. You know, this is 100 volts winding. and this is 400 volt winding, 100 volt, total additive polarity. So this side, how much you will get means 500 volts. This is one possibility. This is step up, and another possibility is step down. Means here you can give source, here you can connect load, or here you can give source, here you can connect load. So two are over here. What's the other connection means? If you reverse any one wind, reversed dot is here, means plus minus minus plus. If you connect like that, they won't add up. So finally the output voltage is 100, here 400, difference is 300. Now this is an auto transformer, 100 by 300. This is called LV common, but subtractive polarity. One more thing, HV as common, additive polarity, HV as common, subtractive polarity. These four connections will give you four different ratings totally. That you have to understand. Here you have to write HV as common, I'll write here, additive polarity. This can be step up, this can be step down, two ways are there. Next, other mode is HV common, subtractive polarity. Now you can see four possible connections, voltage ratios. One is 100 by 500 auto transformer, 100 volt by 500 volt auto transformer, 100 volt by 300 volt auto transformer, 400 volt by 500 volt auto transformer, 400 volt by 300 volt auto transformer. A two winding transformer can be designed, reconnected in these four manners, and each one can be again reversed. Reversed in the sense you can use 100 by 500, 100 across the source, 500 across the load. No, if you have an application where here 500 volt source, if you connect here, you can connect a load. If requires 100, you can use like that also. Total 8 connections are possible. Remember, whether you use this way, whether you use that way, every answer remains the same. This is what I want to convey. Whatever you calculate, rating, power transfer inductively, conductively, windings, currents in the windings, everything magnitude wise, everything is same. Numbers are same, answers are same. One small difference is there. That is, if it is step up, in the common winding, current will flow down. If it is step down, in the common winding, current will go up. Same number, same current will flow in the windings, but up and down. That doesn't make any difference in the answers finally. Now, one simple logic is rating, capacity of each transformer will let us check. You can connect a load here. In simple words, you can connect a load here and you can operate, right? So when you connect a load here, a current will flow, and the current is flowing through this winding. And this winding already had a current rating, and you should not violate it, because it is already designed, pre-designed already. When it was a 2-winding transformer, this was a 400 volt winding, and this 400 volt winding capacity, current carrying capacity, current rating is already 25 amperes. So what is the possible current it can carry means only 25 ampere, not more than that. So you have to connect a load so that 500 volts applied across the load, and the current flow is only 25 ampere. You can't violate it because its rating, its capacity is that. Then you know the transformer rating either V1 I1 or V2 I2, both are same. So simply this is V2 and this is I2. V2 I2. What is V2? 500. What is I2? 25. If you multiply, you will get one number. Let us check finally. Who gives you the best? Once you know which connection gives you the best, in the exam, there is no need of again doing all these possibilities, checking all these possibilities. Directly go to that connection and make it and answer it. That's what my intention is. Next. You can connect a load here also again, so that the current flow can only 25 ampere again, because this is a winding 400 volt winding. 400 volt winding current carrying capacity is only 25 ampere. So again, what is V2 I2 means 300 into 25. This is another rating. Next. Another transformer, auto transformer connection is this. You know the current rating of this winding now. You can connect a load. This load can enjoy 500 volt across it, no doubt. And what is the current you can make possible here is 100 ampere. Why? Because this is a 100 volt winding, and you know 100 volt winding can carry 100 ampere. Its capacity is 100 ampere, which means you can connect a load and you can load. Load means output, out means rating obviously. So that's the reason why I'm putting load, to make a correct sense actually. So when a current is flowing, how much current it can carry? Its capacity is 100 ampere. So what is V2 I2? This is the rating of this transformer connection. Let us move to next. Here also, you can connect a load so that it can carry 100 ampere, obviously. So, what is V2 I2 if you calculate? 300 into 100. I have given you a complete picture of an auto transformer. If a 2-winding transformer like this, 10 kVA, 400 by 100 volt 2-winding transformer is reconnected as an auto transformer, what are all the possible connections? 4 connections I have drawn. It's virtual like 8 you have to imagine, because reverse you can do. You can operate this way, connecting load this side, putting voltage source that side. So total 8 connections. One thing, whether you use this side, whether you use that side, rating remains same. That you know. So totally you can say this is one rating of the auto transformer. This is another rating of the auto transformer, means 500 into 25. This is 12.5 kVA. This is 7.5 kVA. This is 50 kVA. This is 30 kVA. Remember, the beauty of auto transformer is this: without violating voltage rating, without violating current rating in the windings. Remember, after the session, you just take every connection and you can calculate what is the current in the winding. You will notice this winding 25, this winding 100, this winding 25, this winding 100, this winding 100, this winding 25. You will notice this winding 100, this winding 25. You will notice, means without violating current rating, you have to apply KCL here. V2 I2, V1 I1. Simply you will get the answer. You can try it out after the session. So without violating voltage ratings across the winding 400 volt, 400 volt, 400 volt, everywhere 400 volt winding, across that 400 volt only, across that same current only, without violating the voltage rating and current rating, the capacities of the auto transformers are totally different. Of course, this is the worst possible connection. We don't ever think of it, because 10 kVA we are losing it actually. So this is a poor connection, actually worst connection we can say. But if you see the best connection in auto transformer, this is the best connection. What is the best connection means? HV as common, high voltage winding as common, additive polarity. High voltage winding as common, additive polarity is the best connection which gives you maximum rating when it is a auto transformer reconnection from two winding transformer. More theory we have seen already in the class. This is just to make you remind one final thing, that is this: here you will get maximum kVA. Why maximum kVA you are getting? Why not? All the theory we have discussed already. My focus is only on one thing. If you're asked a question on auto transformer where you are going to receive maximum rating for a two winding transformer, reconnection of auto transformer, blindly put this HV. See, where is HV? HV as common, additive polarity, make it, and calculate the rating, and that is the maximum kVA you can receive from an auto transformer. These are voltage ratios: input voltage, output voltage. Voltage rating across the winding don't change. I'm talking about voltage ratios like input voltage, output voltage, because you're connecting like the relative polarities. Definitely secondary, like across the load, voltages will vary. Across the source, voltage will be there, but across the windings, voltages must be same. 400 volt winding, across the 400 volt winding, 400 volt only. The power input to a 500 volt 50 Hz 6 pole 3 phase induction motor running at 975 rpm is 40 kilowatt. The total stator losses are 1 kilowatt. If the total friction and windage losses are 2.025 kilowatt, then the efficiency is. You know the power stage of induction motor already. This is stator input and stator output. That is equal to rotor input or air gap power and rotor output. Finally, shaft output, PSH. Given in the question very clearly, 40 kilowatt is the input of the motor, input of the stator, and total stator losses are 1 kilowatt, which means stator output is stator input minus stator loss. Stator loss is 1 kilowatt, so stator output is 39 kilowatt. Stator output is equal to rotor input because in the air gap there is no loss. So rotor input, once you know, rotor output is slip 1 minus S times. Slip times rotor input is lost as rotor copper loss, remaining 1 minus S times will come out. So rotor output is 1 minus S times rotor input, that is slip is 0.25 because the motor is operating at 975 rpm given in the question. So once you know rotor output, shaft output is rotor output minus friction and windage loss, that is 38.025 minus 2.025, that is 36.025. Finally efficiency is 36/40 into 100. A single phase induction motor draws 12 megawatt power at 0.6 lagging power factor. A capacitor is connected in parallel to the motor to improve the power factor of the combination of the motor and capacitor to 0.8 lagging. Assuming that the real and reactive power drawn by the motor remains same as before, the reactive power delivered by the capacitor in MVR is. This is the previous gate question, as it is I have taken to explain you one concept, that is, when you place a capacitor across induction motor, the power factor of the system will be definitely improved. And the plan here is, from the power factor, operating power factor is 0.6 lagging, the power factor is improved to 0.8, which means definitely the reactive power consumption, in other words, the reactive power asked from the synchronous generators or from the supply bus bars is reduced, because the capacitors will locally generate the reactive power. It doesn't mean that the induction motor is not asking reactive power. They will ask reactive power for their operation to produce RMF. They will ask reactive power. Here, suddenly the power factor is improving means the capacitor is going to provide the reactive power required actually. How much it is providing depends. So according to the question it is given, the power factor is improved. First, the power triangle is this. Phi1, P1, Q1, S1. This was the power triangle first, means when there is only induction motor. When there is a capacitor installed across induction motor, then same P, no change in P actually, because according to the context of question, power remains same. The induction motor working, active power remains same, but what happened is the overall system reactive power demand has been definitely reduced because the capacitor is assisting it. So I will use Q2, P2 is same, obviously S2, and this is Phi 2, power factor angle. So first, cos Phi 1 is 0.6. So Phi 1 is cos inverse 0.6, that is 53.13 degree. Next, second case, after placing capacitor, power factor is 0.8. So Phi 2 is 0.8. Cos Phi 1 is P1 by S1. So already P1 is 12 megawatt. Therefore, S1 is equal to 12 megawatt by cos Phi 1 is 0.6. MVA. This is the first S1. Next, you know sin Phi 1 is Q by S1. So Q1 is S1 sin phi 1, that is 20 into that is 16 MVAR. Think like this. First, there is an industry with an induction motor working. That induction motor has some load on it, due to which the induction motor is asking 12 megawatt power operating at a power factor 0.6 power factor lagging, which means definitely it is asking active power as well as reactive power. So according to the power factor given to you, you can calculate what is the reactive power consumption by the induction motor. If you calculate in this way, the reactive power consumption is 16 MVAR. The active power consumption is 12 megawatt. And obviously the apparent power is in MVA, 20 MVA. This was the first case with a power factor angle 53.13, because the question already contains 0.6 lagging power factor. This is the first original case. Hope you understood this logic. Second logic is, by installing a capacitor, a shunt capacitor, what you are doing is simply, the induction motor is drawing lagging current, the capacitor is drawing leading current, so the lagging component compensates, the leading component compensates the lagging component finally, and the current, net current, vector sum of these two will be definitely nearer to V. That's one logic. Another logic is capacitor supply reactive power. Where it supplies, it assists, it supply reactive power to the induction motor. That's the reason why I used the word locally generating the reactive power. It's not, we can't locally generate active power. We are asking active power from the substation or the distribution transformer, like that we are asking. Reactive power is locally generated by connecting the capacitor. Definitely one thing will happen. The reactive power demand from the supply will be reduced for sure. That's the reason why power factor has been improved. From 0.6 lagging to 0.8 lagging, power factor improved. For example, when you say phi 2 is now 36.87, P2 remains the same. According to question P2, active power remains the same. Definitely, reactive power consumed by the induction motor remains the same. I'm not talking about that. What is the logic here is capacitor will supply some power there. Which power? Some reactive power. So the overall system now with capacitor, the reactive power demand from the system, from the generators, from the substations, like it is reduced, the burden is reduced from that. So that's why I have drawn smaller one. So this is 12 megawatt only, no change. Now previously this is 16 MVAR. Now definitely we're placing capacitor, reactive power demand has been reduced. How much it is, if you want to calculate, proceed the same way and calculate. You know tan phi 2. Q2 by P2. So Q2 is equal to P2 is 12 megawatt as usually into tan phi 2. Tan phi 2 is 36.87. Q2 value is 9 MVAR. Observe carefully. 16 MVAR was the demand by the induction motor first. After placing a capacitor, capacitor will definitely supply some reactive power to the induction motor. That's why induction motor is asking only 9 MVAR. Simple logic. Before capacitor installation, 16 MVAR, power triangle of the system. After capacitor installation, power factor has been improved. Angle is at 6.86. Only 9 MVAR is asked. Demand is this, which means the gap. Previously 16, asking only 9 means definitely 7 MVAR has been supplied by the capacitor. Hope you understood how to deal the reactive power supplement by the capacitor. Sometimes you will be given synchronous condensers or capacitors, anything finally. This is how you have to calculate using power triangle technique. So students, hope this session will help you in your GATE preparation. And I wish you all the very best.